In the realm of scientific progress, transformative breakthroughs resonate and permeate our daily lives by deepening our understanding of the world we inhabit. At the American Physical Society, we take pride in shedding light on the diverse backgrounds, unique journeys, and captivating stories that shape our vibrant community in their relentless pursuit of knowledge and discovery. Since our inception in 1899, APS has been at the forefront of advancing the frontiers of physics, disseminating knowledge across the globe for the betterment of all. In this spirit, APS serves as a beacon, illuminating the lifelong dedication of remarkable individuals in their unwavering quest to impact the world around us. In the ever-evolving landscape of scientific discovery, the future is shaped by early career scientists, innovators who bring fresh perspectives, bold ideas, and transformative approaches. These rising stars breathe new life into the pursuit of excellence. At APS, we are proud to champion the growth, recognition, and success of this dynamic community. The George E. Valley Jr. Prize celebrates an emerging luminary whose groundbreaking work holds the promise of profound impact. This year, we honor Lorenzo Gavasino for contributions to the field of relativistic viscous fluid dynamics that settled long-standing questions about the relation between stability and causality.
My work is more or less to resolve paradoxes, but the kind of problems I approach has this tendency of being obvious because it's true. So I grew up in Italy, in Saronno. In high school, philosophy was the subject I was looking forward to. I have had for a long time a fascination for the big questions. Why does anything exist at all? Why do I happen to be myself rather than someone else? But over time, I began to be more and more concerned about the fact that there was no definitive answer. Eventually, I found that in maths and in physics, instead of asking why of things, you break the why into many hows. Instead of saying why does the apple fall, you say how does it fall? What is the trajectory? What is the speed? And what you discover is that by answering a lot of hows, your perception of reality changes over time. My main motivation, what pushes me, is the goal of understanding where our intuition is tricking us, which is why I get interested in paradoxes, because a paradox is literally a situation where you expect something and you get something else. One paradox emerges from general relativity, because general relativity is the theory that tells us the structure of space and time, right, and how they fold together due to gravity. So the famous paradox is the so-called grandfather paradox, which is based on the idea that if I am a time traveler, I go back to the past, and for some reason, I prevent my grandparents from meeting, then I shouldn't exist because they never met. But if I don't exist, how can I go back in time and make this happen? My result in that paper that attracted some attention was essentially the study of how entropy behaves in a universe where common past and future get mixed. So the standard asymmetry between past and future is broken. So my main contribution to the field of relativistic fluid dynamics concerns a collection of paradoxes that arise when you try to include dissipation and viscosity in a relativistic fluid model. Relativistic fluid dynamics is the study of fluids that move very close to the speed of light, or that are so dense and so hot that their particles wiggle so fast that they get close to the speed of light. And so we need to describe them combining our understanding of fluid mechanics in general and our understanding of the theory of relativity that tells us about how space and time start to behave in a strange way when we get close to the speed of light. And it turns out that when you try to write down some hydrodynamic equations for the motion of viscous fluids in relativity, combining these two things, if you're not careful, it's easy to get nonsensical results. So the standard problem is a fluid that should be, for example, a glass of water that, according to your equations, accelerates spontaneously to the speed of light. Or a fluid that explodes spontaneously without any reason. So it's certainly crucial to approach the scientific process as really a conversation. It's not a monologue, it's a conversation. I propose a way to do things. I explain this paradox for you guys. Now you try to implement this in your simulations or in your theory, in your approach. I like that kind of problem where I can feel safe that whatever happens, my result will be a building block in the tower of knowledge of humanity. So if I could go back in time and speak to my younger self, I would tell him that it's okay to not be able to answer all the questions, but in my life, there will be questions worth answering that I will be able to answer, and those will be enough.
A career in physics is a testament to unwavering dedication, an unrelenting pursuit of knowledge that demands perseverance and passion. When this journey is paired with the ability to captivate audiences, inspire students, and mentor the next generation, a physicist rises to true excellence. The Julius Edgar Lilienfeld Prize celebrates those who not only push the boundaries of physics, but also master the art of sharing its profound insights with the world. In 2026, we proudly present this honor to Hitoshi Murayama for contributions to theoretical and experimental particle physics, as well as inspirational public outreach and effective science advocacy.
The world is what inspires me. When I meet somebody I didn't know before, I tell them that I'm a theoretical physicist who is trying to understand who I am, where we come from. That's the age-long question of humanities. Anybody would like to understand this. So I hope that I can convey questions in a way people can relate to. I'm Japanese. I grew up in Japan, but the part of my childhood actually lived in Germany for 4 years. If you drive for 1 hour, you are in Netherlands, different currency, a different system, different language. So that kind of environment was really, really fascinating. I was just a really curious child who asked a lot of questions to parents. When I put my feet into a swimming pool, my legs look shorter than they are. So why is that? Why is the sky blue? But eventually, I get to the point that, okay, this is how far we understand things. Beyond this line, we don't understand anything. And that's where, science starts, like dark matter of the universe, dark energy, how we survived the Big Bang. All these questions don't have answers right now, but I might be able to help. So once I have learned the basics of physics, I see physics literally everywhere. Our body is made of the debris of the stellar explosion. We are literally made of some pieces of the star. So the one thing I always try to make physics fun to the general audience is to really make it sort of connected to what we do in daily life. And the way we can talk about why the sunset is orange, why is the sky blue, why do the leaves change color in the autumn, and all of these things have to do with physics. I have done public lectures pretty much all over the world, ranging from South Africa, Europe, Australia, Japan. They have different cultures. But the kind of questions I ask, why do we exist, where we come from, anybody seems to be able to relate to those questions. I lived in West Germany because it was still a divided country. And I had an opportunity to visit Berlin. There's a wall, there's a watchtower, there's a minefield. And after that, we still saw ruins left over from World War II. It's just a totally different world. It was really shocking for a child. But even during the time of Cold War, scientists from Soviet Union and on Western Europe really worked together on many projects. So science definitely goes beyond borders, and world really can be one. Now I live in the United States and worked on many different continents in my career. So I really became appreciative of having the diversity of different cultures and languages. But at the same time, I also appreciate that we have common goal. We are trying to understand the universe we live in. We are trying to understand where we came from. And that's really common to the entire humanity. I think the best paper I've ever written was actually working with a student, Haruki Watanabe. He pointed out that something I explained in my class was wrong. He pointed at me and said, "Professor, you're wrong." I was appalled when he was pointing that out to me in front of everybody. But after the class, when we sat together and talked about this, realizing that I'm missing something important was actually a great feeling. Once again, you are at the frontier, at the boundary between what I understand and what I don't. So that's the biggest satisfaction I have as a scientist, that we do understand things, but we also have limits. And beyond that, we still have to work on.
The APS Medal for Exceptional Achievement in Research represents the pinnacle of scientific excellence. It honors contributions that have reshaped our understanding of the intricate fabric of the universe. As the most prestigious accolade of the American Physical Society, this medal is awarded to those whose lifelong dedication to discovery has left a profound and lasting impact on the field of physics. In 2026, we proudly confer this honor upon Francis Halzen for contributions to the field of neutrino astrophysics, especially leadership of the IceCube Neutrino Observatory and the discovery of high-energy astrophysical neutrinos and their sources.
Nobody ever told us this is uninteresting. Many people told that it would never work. So we were off chasing ghosts, literally in this case. I was a particle physicist about half of my career. Neutrinos came later, in the mid-80s. I had a postdoc, and he had the idea to start investigating how we could build big neutrino detectors that would detect neutrinos from space. The first paper in the late 70s predicted you need a kilometer cube detector. And since then, theorists in large numbers, including myself, would try to do calculations of what the yield of neutrinos would be in these sources, mostly inspired by the problem of cosmic ray sources. The problem with cosmic ray sources is we didn't know what they are and how they work. The neutrinos tell you where cosmic rays are produced. So what are neutrinos? They're different messenger of the universe. Fortunately, they have a very small probability of interacting with matter. But if they crash into an atom, they make light. And we detect that light, and this light pattern tells us everything about a neutrino. And so you have a telescope. Every neutrino is a dot in the sky. You put them together to make a picture of the universe. And hopefully you see the sources of the cosmic rays emerge from the picture. You know, everybody thought this was a cute idea that probably didn't work, and they were right. I had been thinking about this project and giving talks for a year or two, and I get one day a phone call from the director of polar programs of the National Science Foundation telling me we have caught 2 Berkeley physicists doing an experiment with putting photomultipliers in boreholes, and that experiment was not approved. And everybody has told me that you are behind this. The truth was, I had no idea. I had never heard about them. I didn't know who they were. But during the conversation, I told the director of polar programs what was behind this. And he thought this was pretty interesting. And so that was the start of the collaboration. Even when we started building the ultimate ice cube detector in 2005, it was still not a given that this would succeed. We had no idea what the optics of the ice was. We had no idea whether we could scale up the drilling. We had no idea whether we could look through the background of the neutrinos from the atmosphere. And then we had to be lucky enough that the flux was large enough so that a kilometer scale detector would do the job. I saw this whole thing happen through a telephone call now and then and over email. It was not always going well. It was a roller coaster even during the 5 years of construction. The first event we saw was a neutrino coming right up against a string of photomultipliers. And I remember recording the times on graph paper with a pencil and plotting the times the light arrived at each photomultiplier and derived the speed of light. And then, well, we detected a neutrino. A few weeks after the paper came out, we were declared the 2013 Physics Breakthrough of the Year. Clearly, there was a lot of interest. This astronomy is in its infancy. I just want more telescopes, more neutrinos. Besides solving the cosmic ray problem, we will see some real surprises. Collaboration in this was everything. We had a very talented group covering every problem. We let them do their job.
Hey, I'll look up here.
The great joy of doing science is learning things. You know, you suddenly learn things that you would never thought you could understand. And that's the real joy when you wake up in the morning of doing science.